So because of the internet connection, it was disconnected. Is it visible?
Yes, sir.
Rule number 20, 23, 38. So once again, I will write the given data they have given here. K equal to, what is K equal to? How much it is? K equal to 12 into 10 to the power of minus 6 Newton meter per radian. K is given. L is given as 10 plus 5 theta minus theta square into, that is called microhenry. I'll use directly microhenry only, I'll use. And here the current I is given as 5 ampere. The current I is given as 5 ampere. And we know the formula, that is we have to identify theta here. So the angle of deflection theta equal to 1 by 2 I square divided by K dl by d theta here. So we know the value of L, then by differentiating this L with respect to theta, we'll get dl by d theta. So dl by d theta equal to, tell me the differentiation of 10. Any one of you?
0.
Differentiation of 10 is 0 here. So why these peoples will join later? Just a minute. We'll increase the sound. Differentiation of rule number 8. What is the screen? Which screen is visible here now?
Yes, sir.
So differentiation of 10 is 0 plus differentiation of 5 theta.
5.
Differentiation of 5 theta equal to 5 minus differentiation of theta square.
2 theta.
2 theta, it is plus or minus?
Minus.
Minus 2 theta. We can call that one here now. We can call that one. Just a minute. Yeah, what is go? Next, what we have to do? We have to enter here into micro Henry. No, it is. The L is in micro Henry. They have given here now. So into this is 10 to the power of micro means how much it is? 10 to the power of minus 6. So this equation you can directly write as 5 minus 2 theta into 10 to the power of minus 6 Henry. You can substitute here. Next, 1 by 2. What is the I? That is called pi square. The K is 12 into 10 to the power of minus 6. And dl by d theta equal to 5 minus 2 theta into 10 to the power of minus 6 here now. So here also 10 to the power of minus 6 is there. Here also 10 to the power of minus 6 is there. It will get cancelled here now. So 1 by 2 into 12, how much it is? 2 into 12, that is called 24. And 5 square, how much it is? 5 square is nothing but 25.
Yes.
5 minus 2 theta, 5 minus 2 theta. That is called theta here now. Next you substitute here now. 25 into 5. 25 into 5. 125 minus 25 into 2, 50 theta divided by 24 here. What you do, this 24 you send into LHS side, it will become 24 theta. So 125 minus 50 theta, we can write like this. And next what you have to do, this minus 50 you send into that side. So it will become plus 24 theta plus 50 theta equal to 125. 125. 24 theta plus 50 theta, how much it is? 74 theta, 125. So theta equal to 74 divided by, 125 divided by 74. So not 74, it is 125 divided by 74. How much it is?
1.68.
1.68 radians. We can call that one. 1.68 radians here. See here, some people they are joining actually B. Once I have connected the plate means it is difficult. Roll number 28 is joining now. So this is the solution we have performed for the problem on EMMC. I will show the actual solution for that. It is already displayed here. 1.689 radians it is. 1.689 radians we have calculated here. So for that reason only I will tell that one, first you have to read the question carefully. Once you write the given data, then you can just substitute in the formula which one is unknown, which is not given, and in the given we are going to get that value or not. You have to identify. Same thing they have written here now. L they have given here now, but dl by d theta we have calculated here now. So next from the deflecting torque formula we have written here, TD equal to 1 by 2 I square dl by d theta. I is given, dl by d theta we have calculated. Just substitute here. You will get the deflecting torque. Next we can apply the formula for deflecting torque equal to controlling torque. So we know the TD value here now, we calculated. Then the controlling torque equal to k theta here now. Theta is the unknown value, k is already given, theta equal to TD divided by k. Obviously we'll get that one. So the theta equal to 1.689 radians we have given here now. How many of you solved? Raise your hand. Same answer hai kya? Raise, you can raise your hand. Only one person, roll number 13. Other people's, what you were doing? Yesterday only I have given the problem. Nobody have solved means that is actually a terrible thing. You have to solve these problems. You have to practice this one. They will give that one 1.6, 1.7, 1.8 like that. 4 options they will give by giving the problem. Even it may come in the ISC also. Okay. So it completes the moving iron instrument here. The moving iron instrument numericals it has completed. So the next part will go, that is called the EMMC. We are going to call that one. Dynamometer or EMMC. EMMC is nothing but electromagnetic moving coil instrument here. So what is the difference? Have you tell the long form of PMMC? Can you tell me, anyone?
Permanent magnet moving coil.
Permanent magnet. Here which coil we are using here now? Electromagnet we are using here now. Instead of permanent magnet, we are using electromagnet moving coil instrument here now. For electromagnet, EM we have used, moving coil EMC we have used here now. So that is EMMC we are going to call here. This instrument is actually, it is used for the measurement of voltage, current, and it is also used for the measurement of power also. This instrument, from this instrument, you can also measure the power also here. You compare with PMMC and what is that, moving iron instrument. Only voltage and current we were measured in that from those instruments. But from the EMMC, we can measure, this instrument can be used for the measurement of voltage, current, and power. All three electrical parameters we can measure by using this one. So the main difference between the PMMC instrument and this EMMC instrument is that the permanent magnet is replaced by electromagnet. In the permanent PMMC instrument, we were using the permanent magnet, but that is replaced by the electromagnet. All other things are same. Understood? And one more. So this is the just principle or whatever we have corrected, that difference between PMMC and other things. Next, once we will go for the construction of EMMC, mainly this instrument, it has two coils. Two coils it has, two coils. One is fixed coil, and another one is moving coil here. Fixed coils, whatever the permanent magnet is replaced by the electromagnet here. This is fixed coils. Two coils we are using here. One coil, fixed one, another one is moving coil. But what we have done in the construction, while doing the construction, this fixed coil, whatever the turns are there, we have split it into two equal parts here. Two equal parts we have split it here. One coil I will keep here, another coil I will keep here now. In between these two, half of the fixed coil, I am going to place the moving coil here. This is the construction here. Mainly the EMMC instrument has two coils only, fixed coil and moving coil. But while doing the alignment or construction, the fixed coil is equally separated into two parts. So in between this half of the fixed coil and another half of the fixed coil, we are placing a moving coil here. The moving coil, that is, we are placing over there. So that one only they have mentioned here. Now a fixed coil is divided into two equal parts. Two equal parts or two equal coils we have divided here now. So the moving coil is placed in between two half of the fixed coil here now. The moving coil is placed between two half of the coil here now, fixed coil here. Both fixed coil and moving coils are air cooled here now. Air cooled means just a wire wound we are using here now. We are not using any iron material or core material, we are not using here now. So this is air is acting as a core here now. See here, एक wire लेते हमने ऐसा wound करके रखते. This is called air cooled, we are going to call. In between this one, we have used the iron part. Suppose you consider this one as iron part. इसको मैंने winding किए. That is called iron core, we can call that one. But there is just, I will winding that one, I will remove this iron part. The air is there inside, that act as a core for that reason. So we are not using any iron part materials here now. So these both moving coil and fixed coils are air cooled coils we are taking here. Because of this iron part removing, the hysteresis effect will be zero here. Whatever the losses are there, the iron losses, that is hysteresis loss, that effect will be zero here. So, but the spindle is connected to the moving coil. The spindle is connected to the moving coil here now. So that one, the spindle is also connected to the spring of for the controlling to produce the controlling torque, and we are using the air damping method for this EMMC here now. For the damping force to produce the damping torque, we are using the air friction damping we are using here now, and spring control method we are using here now. The pointer is attached with the spindle in a non-metallic here now. We are not using any metallic farmer, or we are not using any core material here now. So the moving coil is wounded here now. It is wounded. So this is the construction of EMMC instrument. This is the construction of EMMC instrument. I will go to the diagram here now. Just look at the diagram here now. See here. This is wire wound is visible here now. I will take the annotate. See here, the positive or negative or phase and neutral. It is applicable for both AC and DC. This coil is applicable for both AC and DC. While working principle explaining, I will tell that one here now. See here, this is one fixed coil, half fixed coil, another half fixed coil I have connected here now. In between this, the moving coil is placed here. Either a half fixed coil, another half fixed coil. In between these two half of fixed coils, we have placed a moving coil here. No? We have placed a moving coil here. See, is there any core material here? No. Simply we have taken a conductor. We have make it as wound here. No. See here. There is no iron core material at all here. So inside that, from one conductor to another turns, there is a air is acting as a here now. That is core material here now. For that reason, air cooled coil we are considering this one. The fixed coils are air cooled here now. Both fixed coils and moving coils are air cooled only. We are not using any core material here now. So half of the fixed coil is placed at left side and half of the fixed coil is placed on the right side. In between these two half of the fixed coil, we have placed a moving coil here. So see here, both these half coils are connected in series only here now. Same supply will flow here. The same supply will connect to the both the half cycles here. And this, the scale is connected here. Inside this one, we are using a spindle. This spindle is connected to the pointer, as well as some spring methods also we are using here now. And air damping, that is frequency air damping torque production method is there. So air damping, the air rod is also connected, that is to the this spindle only here now. Okay, this is the pointer. That's just I am telling the construction here now. And this scale is, it is going to indicate over a calibrated scale here. Now we are using this calibrated scale here now. Okay, the working principle is very important here. Working principle here. Whenever we'll give the supply to this fixed coil here now, see here, the current will start to flow in this half of the coil. Okay, so the magnetic field will be produced here, it will flow, and same current it will flow through the another half of the coil. So magnetic field will be producers in between these two coils here. The magnetic field, electromagnetic field will be producers in between these two coils here. So because of this electromagnetic field, whatever the flux density will produces here, that is equal to this current of the flowing in the fixed coil here. You can tell that. See, this circuit is not ended here. The same current, it will flow through the moving coil also through a brushes. Through a brushes we have connected here now in the constructional. So it is same current, it is applied to the moving coil also. Because of this, in between two magnetic field or electromagnetic field, a current carrying coil or a conductor place remains, it will produce a torque or not. The mechanical force will be produces here now. The simple basic statement we are using here now. In between the electromagnetic field, we are placing a current carrying conductor. In a moving coil, we are passing a current here. Same current is flowing here. Yes? Yes or no? So the force will be producers. Force will be producers means the moving coil will start to deflect here now, which is attached to the spindle. If the moving coil is force is rotated, rotation will start as, then the pointer will start to rotate here. So this is the working of the EMMC here. This is the working of the EMMC. Same thing we have written here now. When the current flows through the fixed coil, it produced a magnetic field here now. The magnetic field will be producers in between two fixed coils, whose flux density is proportional to the current through a fixed coil. The flux density, the flux is produced. The flux density is flux per unit area. Yes, that flux density is directly proportional to the current flowing through the fixed coil. You can see here now. So the moving coil is kept in between these two fixed coil. Half of the fixed coil we have placed here now. In between that two half of the fixed coil we are placing here. We have already placed the moving coil here. When the current passes through the moving coil, same current will flow through the moving coil. Then magnetic field is produced by this coil also. So that magnetic poles are produced in such a way that the torque produced in the moving coil, that is called, it is going to deflect the pointer over a calibrated scale here. So it is also going to produce a magnetic force such that the mechanical force or whatever the torque will be produces in the moving coil, which is going to deflect here now. So if it is deflected, the pointer is also, so whatever the spindle is connected to that coil only. So spindle is also connected to the pointer. If the spindle will start to rotate, then the scale will rotate or move over a calibrated scale here. So this instrument, I told, it is going to work for both AC and DC. Just now I told it is going to work for both AC and DC here now. How it is possible here now? See here, the current direction here, it is going here positive to negative. All the current direction in the fixed coil and moving coil here now. Same only. Same current is flowing here. Yes or no? Same current is flowing here. The current will start to flow here. Here it will flow. Same current it will flow through the another half of the fixed coil. Then the same current will flow through the moving coil here now, and then it will go back to the negative, positive and negative. For the positive half cycle. For the negative half cycle, the current will reverses here now. The force will be also reverses here now. It is going to, so not force will reverses. The current direction in the both fixed coil and moving coil will be changes here now. Yes or no? Both, it is the current direction in the moving coil is not different in the as compared to the fixed coil here now. In the both the coils, the current flowing through that conductor or coil is in the same direction here now. When the current in the fixed coil reverses, the current in the moving coil also it is going to reverses here now. So when the both the coil current is reverses, means the torque will remains in the same direction. Since the current I1 and I2 reverses simultaneously, I1 we are going to consider as current flowing through the fixed coil, and I2 we are going to consider as current flowing through the moving coil here now. If the current direction will reverses in the fixed coil, means the current direction of the moving coil also changes here now, reverses here now. So both are in the same direction, then the torque remains in the same only here now. Yes. So for that reason, it is applicable for both AC and DC, we are telling here now. It is applicable for both AC and DC here now. This is because the fixed and moving coils are either connected in series or parallel. You can connect it here, it is connected in series. You can connect this one in parallel also. I'll tell in the later operation will be there. That is the EMMC instrument we can use as ammeter, voltmeter also, and wattmeter also we can use this instrument. Can use this instrument as ammeter, voltmeter, and wattmeter also. You can use this instrument. Is it clear? Any doubts you have? You can ask. If you have any doubts, you can ask. Very simple operation is there. Same like a PMMC, but only thing is that here we have not used permanent magnet. Any doubts?
No, sir.
No doubts. Okay, then the construction and working principle is over now. Next, we will go for the torque equation of the EMMC instrument. So, from this instrument, what is the torque developed here now? We are going to measure here now. The torque equation of our torque developed by the electromagnetic moving coil here now. See here, this is the fixed coils we are using here now. That is one fixed coil is there, means half of the two. One half coil fixed coil, that is F1, F2 we are going to use here now. Actual circuit diagram we have drawn here now. So that is, this is fixed coil. This one we are considering as moving coil here now. Okay. So the inductance, that is self-inductance of the fixed coil is considered as L1, and self-inductance of the moving coil is considered as L2 here. Self-inductance of fixed coil is L1. self-inductance of the moving coil is L2, and this fixed coil and moving coil in between that one, whatever the mutual inductance is there, that is we are considering as M. We are considering as M. So the current flowing through this fixed coil is considered as I1, and current flowing through the moving coil we have considered as I2 here. Is it clear? The representation I am telling here now. This is fixed coil. It has two parts, F1 and F2. Okay, total fixed coil F we are going to consider. This F is divided into two parts, that is F1 and F2. So the total coil, that is the self-inductance of the fixed coil is L1, and self-inductance of moving coil is L2. In between this fixed coil and moving coil, whatever the mutual inductance is there, that is called M we have considered here now. And current flowing through the fixed coil is I1, and current flowing through the fixed moving coil is I2 here considering here. That one we have written here. L1 equal to self-inductance of fixed coil, L2 is self-inductance of moving coil, M is the mutual inductance between the fixed coil and moving coil, I1 is the current through fixed coil, I2 is current through the moving coil. Is it clear? This one? So what is the total inductance? How can we write the total inductance here now? Total inductance L. You can write like this. How we can write total inductance? That is called L equal to L1. We can write first self-inductance of this one. Yes? Is it audible or not? Hello. L1 plus L2. This mutual inductance of this one and this one here now. How many coils are there? Two coils are there. Though both are connecting together here now. M plus M, that is called 2M here. That is called total inductance of this instrument here. It is combination of a fixed coil, moving coil, and combination of both here. That one we have written here from this circuit diagram we have considered here now. The total inductance of the system is L total, or L equal to L1 plus L2 plus 2M we have considered here. But we have already derived the derivation for the moving iron instrument. The torque developed equation of the moving iron instrument we have already derived here now. From that equation, we know the deflecting torque equation, that is called TD equal to 1 by 2 I square dl by d theta. This formula only we know we have derived and we have used it just now. We have used it for the solving the problems also. Yes. This equation I will consider as equation number 1. I will consider as equation number 2. From the moving iron instrument, the torque developed in the moving iron instrument, I will substitute as equation number 2 here. Equation number 2 here. Substituting equation number 1 in equation number 2, we get here now. In this place of L, you substitute this L1, L2 and 2M here. L1 and L2 and 2M you substitute here now. So TD equal to 1 by 2 I square I will keep as it is here now, d by d theta. In the place of L, what I will substitute? I will substitute L1, L2 and 2M. L1 and L2 and 2M. From this fixed coil and moving coil here now, the self-inductance values are independent of theta. It is not depending on the theta. But the angle of deflection depends on the mutual inductance only. So for that reason, L1 and L2, we are the differentiation with respect to theta, that is called 0 here now. The differentiation of L1 and L2 is 0. The differentiation of L1 and L2 are 0. But the 2M, the angle of deflection is considered here now. So with 2 the mutual inductance only, the deflection will vary. So dm by d theta we are considering here. So these are independent of theta, means it is act as a constant value here now. Suppose L1 is 2 microhenry is there, 3 microhenry is there. 3 differentiation of 3 with respect to theta, what is the value? What is the value? 0 only, na? Yes or no? I'm asking to you people only. Try to give the reply. Roll number 2. We have joined now only. Prachi, Bosle. You people are not ready to reply means why I have to waste the time then. I simply explain and leave that one. So that is 0, 0. So d2m by d theta here now. So 2 dm by d theta. This 2 will get cancelled here now. 1 by 2 into 2, that is called 1 only. So Td equal to I square dm d theta. The deflecting torque we have calculated here now. That is the final torque equation of EMMC we are going to call that. This I is nothing but we are considering this I is that is called the current flowing in the fixed coil and moving coil. Both are same only na here. So we can write this one as I1 into I2 here now. For the series connection, I1 into I2 dm by d theta. Dm by d theta here. Dm by d theta. In the next slide, it is there already. Just a minute, I'll take that. See here. If the coils are in series, that is called I1 is not equal to I2. Both are series only, but the currents are not equal. I1, the current flowing through the fixed coil is different, and current flowing through the moving coil is different. On that situation, the deflecting torque we are going to consider as I1 into I2 into dm by d theta here. I1, I2. If both are same, the fixed coil current flowing through the fixed coil and moving coil, then we can use that is I1 and equal to I2 equal to I. On that situation, I square only it will come. Na? In the place of I1 you substitute I. In the place of I2 you substitute I. I into I, that is called I square. I square dm by d theta. That is the standard equation here. So this is the torque developed in the EMMC here. So we already know that one, the controlling torque equal to the deflecting torque. So the controlling torque is nothing but TC equal to K theta here now. So TD equal to I1 I2 divided by into dm by d theta here now. So TD I will substitute I1 I2 dm by d theta. This K you send into RHS side, it is divided by K here now. So theta equal to I1 I2 dm by d theta. Hence the deflection of pointer is proportional to the current passing through the fixed coil and moving coil here. Now it is not only depends proportional to the current flowing through the fixed coil. It is depends on both fixed coil and moving coil current here. The I1 is current flowing through the fixed coil. I2 is current flowing through the moving coil here. So this angle of deflection theta is depends on both the current passing through the fixed coil as well as the current passing through the moving coil. Current passing through the moving coil. So it completes the torque equation of the EMMC instrument here. If you have any doubts in the construction, working and torque equation, you can ask. If anyone have the doubts, you can ask.
No, sir.
I asked you, you have any doubts, you have to reply. If yes, you can ask the question. If no, at least you would reply that one. No, sir, बोल के. क्या सावन सर आपका स्टूडेंट कुछ रिप्लाई नहीं देते. Is it audible or not? 28 students are there. Out of 28 students, nobody is replying.
Yes, sir.
अच्छे से खाना खाए, नींद आ रहा है, शायद नींद कर रहे हैं सब लोग ज्वाइन करके, मीटिंग ज्वाइन करके, ऐसा तो नहीं है ना?
No, sir.
नो। देखो एक ही रोल नंबर 2 रिप्लाई दे रहे हैं, बाकी सब सो गए अभी, बहुत गहरे नींद पे है, नींद पे है। So we'll go for, this is the TARC equation here. No, I told, see here, comparing with the, actually the PMMC instrument, the angle of deflection is directly proportional to the current. But in the moving iron instrument, the scale is not uniform because the theta was directly proportional to the square of the current. Here, the deflection is proportional to the current passing through the fixed coil and moving coil. We are going to, both it is depends here now. So it has some advantages and it has also some disadvantages are there. What are those advantages and disadvantages? We are going to discuss here. It can be used for voltage measurement, current measurement, and power measurement here. That is first advantage. It can be used for voltage measurement, power measurement, current measurement. So we are not using any iron material here, no, core material. So air core material we are using here, no, air is act as a core here, no. So air core coil we are using. Because of this, the iron losses are like hysteresis and eddy currents are 0 here. There is no iron losses. For that reason, the second the advantage is hysteresis error is nil, and third advantage is eddy current error is nil here. And we are using the air damping method here now, so that damping is effective here. It can be measured correctly and accurately the RMS value of the voltage, means it is applicable for both AC and DC also. It is applicable for both AC and DC, and it can be used for the measurement of voltage, current, and power. Okay, and it has some disadvantages also. So the disadvantages are like the, what is that one here now? The scale is not uniform. Theta is directly proportional to I to nahi hai, because current flowing through the fixed coil and moving coil both are different, means it is not uniform only. Scale is not uniform. It will consume more power or high power we are going to consider because of the high resistance of two coils here now. The cost is more, and error produced due to frequency, temperature, and stray field here now. After viewing the supply also, some electromagnetic field, in that one some stray field will be there, so that, and the temperature and some frequency variation, the AC we are applying, means some errors will come over. Okay, and torque weight ratio is low because field strength is very low here now. This is the, these two are the main disadvantages of this instrument. So PMMC instrument, advantages and disadvantages. Next, we'll go for, there are three cases are there. First case, how we can use this one as emitter connection. Second case, how we are going to use this instrument as a voltmeter. And third case, how we can use this instrument as a wattmeter here. So case one, we are going to discuss here now. Case one, we will discuss here now. See here, whatever the electrodynamometer EMMC instrument working principle we have discussed just now, the same circuit we have used here. Okay, so some swamping resistance we have used here now to swamp the currents and all the things here now. See here, half fixed coil is connected here, another half is connected here, and the moving coil is placed in between this half fixed coil, but it is connected one parallel branch we have connected here. We have connected one parallel branch, and in between this fixed coil we have used one shunt resistance we have used here. The shunt resistance is used here. I think how many of you have you were there for the shunts and multipliers for the range of extension of PMMC? We have used shunts for the increasing the range of ammeters, multipliers for the range of voltmeter. Same method like that we are using this method here now. So electrodynamometer as emitter, we are going to use this connection here. So that the simplified modified circuit diagram we have drawn here like this. So here the moving coil is there, here fixed coil is there, and one shunt path we can connect for the extension here now. The value is designed such that current flow through the moving coil and fixed coil here. RSH is designed such that equal current should flow through the moving coil and fixed coil. We have to help that current flow through the moving coil should be equal to the current flow through the fixed coil here now. For that reason, whatever the extra current is there, we can bypass by using this RSH here. So same thing you have written in the explanation here now. The moving coil is connected in series with the swamping resistance across a shunt together with fixed coil here. Together with fixed coil here now. Fixed coil is also connected here. Moving coil is also connected here. Thus, there are two separate parallel branches for fixed and moving coil here. This connection, it is a parallel connection or series connection? This one, the fixed coils, parallel connection only. So two separate parallel branches are there, one for the fixed coil, another for the moving coil here. In order that the emitter may indicate correctly at all frequencies. So in order to, the emitter should indicate that for all frequencies, we are telling that one. So currents in the fixed coil and moving coil must be in phase here. Both should be in phase, means both should be in equal. There is no phase difference at all over there for the, so the currents in the number 12, current in the fixed coil and moving coil must be in phase. Why these people are left? Number 34, 13, 12. Fixed coil and moving coil must be same. This requires time constant that is called L/R ratio of two branches to be equal, as otherwise the current in the two branches will not be independent of frequency. See here some inductance are there, some resistances are there here now. L/R ratio should be same here now, that is constant. This requires the time constant L/R of two branches to be equal here now. The inductance of this coil and inductance divided by resistance and inductance divided by resistance of this coil, these two coils should be equal. Then only it is going to U for all frequencies here now, independent of, it will not be independent of frequency here now, otherwise. So fixed coil and moving coils are connected in parallel for emitter connection, and these coils, the coils are designed such that the resistance of each branch is same here now. If the L/R ratio is same and resistance is same, then current flowing through this I1, moving coil is I1, current flowing through the fixed coil is I2, you are considering here now. So both are same means, then what is the current? This I1 and I2 will be same only. The branch resistance is same, L/R ratio is same, then we can say that the current flowing through the moving coil is equal to the current flowing through the fixed coil here now. Yes or no? Fixed coil are connected in parallel. Fixed coil and moving coil are connected in parallel for emitter connection. Emitter connection के लिए दोनों parallel में है. But the coils are designed such that the resistance of each branch is same here. Resistance of each branch is same here. Then the current will be also same here. Yes or no? If the resistance is same, then therefore we can call that one as I1 equal to I2 here. Now to extend this range, suppose हमने 5 ampere का emitter range use किया है here. Okay. Yes. Who is that? Namrata? Okay. So suppose this one only you consider. Suppose I want to extend the range of EMMC. EMMC range extend करना है. Then what we have to do? We have to connect one parallel shunt resistance here now. Then whatever the extension of current is there, the extended range of out of range, that is called more than the rated current here now, it is going to bypass here now by connecting one small value of shunt resistance here. Now we can bypass the current here now. That one we have to again calculate. Same multiplication formula is there, multiplication factor of the that is PMMC. Since we have used the same formula, we have to multiply here and we have to calculate the total current I we can calculate. To extend the range of current, a shunt may be connected in parallel with the meter. This moving coil and fixed coil, it is a moving that is a meter part only, na? This moving coil and fixed coil, these are the instrument parts only. But whatever this shunt resistance we are adding here, that is extension range. To extend that one, the outer circuit we have designed here. From this one, we have to calculate the multiplication factor here. Now that multiplication factor we have to multiply to calculate the total current I here. Now we can get that one, or we can increase the range of the emitter also here. The value of RSH is designed such that the current flows through the moving coil and fixed coil here. Like that we have designed here. So we'll stop here only. The case 2 is there, that is for the emitter connection. We'll discuss in the next class. See here, one more formula. Just a minute, it is not ended. So if current I1 equal to I2 equal to I, and the deflection is phi, the phase difference is 0, both are in phase, that is phi is 0, then TD equal to I1 into I2 dm by d theta, whatever the torque equation we have used, that is. So I1 is equal to I2, so that one I into I, that is called I square dm by d theta we can use. And according to the formula of TC equal to TD, we can use TC equal to K theta here. No, so K theta equal to, that is theta equal to I square by K dm by d theta we can use here. No, so see here, this is K is constant, this is mutual inductance is also N, consider that one. So theta is nothing but angle of deflection. For angle of deflection for emitter angle, that is the angle of deflection is proportional to the square of the current flowing through that coil. Square of the current flowing here. For that reason, we can say that the scale is not uniform here. If theta is directly proportional to I, then the scale was uniform. But the theta is directly proportional to I square we are getting here. Now the scale is not uniform here. Which connection we are using here? Emitter connection. For the emitter connection, the deflection we are measuring from in the form of I. For the old meter, we have to consider theta should be proportional to V or V square. And for the watt meter, theta should be proportional to the VI. We can call that one VI or I square or whatever it may be. In the form of power formula should have to come in. For the emitter connection, so the current in the form of current, the deflection we are defining here. I square is directly proportional to theta, or angle of deflection is square of the current. We can say that one here. So I'll stop here only and we'll continue in the next class. Just a minute, I will note down the roll numbers. 2, 3, 4, 5, 6, 7, 9. L1, roll number L1. (16). Roll number 16, are you there? 15, 16 is that, okay. 17, 18, 19, roll number 19, roll number 21, 25, 27, 29, 31, 35, 38, okay, 36, 37. Okay, and here only, and in the next class we'll discuss about the voltmeter connection and wattmeter connection. We'll discuss that one.